Hi to everybody. In this lecture video, we are going to be focusing more on chapter 28. And chapter 28 is about direct current circuits. And after doing this chapter, you will be able to find an expression for the resultant equivalent resistors for combination of resistors in series and in parallel, and you will also be able to state the Kirchhoff's law for direct current circuits, and you will also be able to know the sign convention used in the analysis of this kind of circuits, and you will also be able to solve the problems relating to the above or to the direct current. Right, let us just start by defining the direct current. The direct current is when the current in a circuit has a constant direction. The current is called direct current. Most of the circuits analyzed will be assumed to be in a steady state with constant magnitude and direction. Because the potential difference between the terminals of the battery is constant, the battery produces direct current. Now, the battery is known as a source of an EMF, the source of an electromotive force, and we normally call the electromotive force the EMF, and we denote the EMF by this symbol epsilon. Now, the EMF of a battery is the maximum possible voltage that the battery can provide between its terminals. The EMF supplies energy. It does not apply a force. I just want to repeat that again. The EMF supplies energy. It does not apply a force. The name electromotive force is just a name. It has nothing to do with the force, but it just supplies the energy. Now, the battery will normally be the source of energy in the circuit. The positive terminal of a battery is at a higher potential than the negative terminal. What does that mean? It means that, for an example, when we draw the symbol for a battery, I think you know that we normally use this vertical two lines, but each and every time one line is higher than the other one. That means that the positive terminal is always bigger, or is always higher vertical line compared to the negative terminal. So that's what that statement is saying. Right. Now we consider the wires of or the connecting wires in the circuit to have no resistance. Right. Now, if the internal resistor is 0, the terminal voltage equals the EMF. For an example, in a real battery, there is an internal resistance. For example, if you can take this shaded area here as your battery with a certain EMF as well as the internal resistance R. Now, the change in the terminal voltage, change in V, is just equals to EMF minus IR, the current times the internal resistor, where this minus here is actually being used because when you put there will be a drop in the voltage for when you pass through the resistor. You'll just see when we do the Kirchhoff's law. Now, that's what you are going to have. And I also want to remind you that you remember that the change in V can also be related. The change in V can also be related to the load resistor by this equation. So as a result, if I rearrange that equation, I can, whenever I see change in V, I can just write this IR. Right. Now, when you rearrange the equation and you want to make E a subject of the formula, this is what you are going to have. When you rearrange the equation, this is what you are going to have. Right. Now, what is the current? Whenever you want the current, you rearrange the equation and then you divide by R plus small r on your right hand side, and then the current can just be given by this. Now, when you rearrange that equation again, in order to get the power, what are you going to do? You are just going to have EMF is just equals to I times R plus I times small r. But now if you multiply by I in both sides of the equation, this is what you are going to have. You are going to have I squared on the other side. But what is this? This is nothing, but this is just the total power. the total power, which is nothing else but the power delivered to the load resistor plus the power delivered to the internal resistor, which is denoted by the small r. So that's what you are going to have when you rearrange that equation. So this is the total power, and that is the power to the load resistor. That is the power delivered to this resistor, and that is the power delivered to that internal resistor. Now the EMF is equivalent to the open circuit voltage. To this is the terminal voltage when no current is in the circuit. This is the voltage labeled on the battery. The actual potential difference between the terminal of the battery depends on the current in the circuit. Right, now let us also talk about the load resistance, as I've already introduced you. The terminal voltage also equals the voltage across the internal resistance. That change in V is just equals to I times big R. This external resistor is called the load resistor. In the previous circuit, the load resistance is just the external resistor. In general, the load resistance could be any electrical device. This resistance represents the load on the battery, since it is supplies the energy to operate the device containing the resistance. Right, now in terms of the total power, as I've already explained to you in the whiteboard, that the total power is just given by I change in V. From the previous chapters, we have seen that this is the total power, and in this case it's nothing else but it's just the current times the EMF. Now this power is delivered to the external resistor, or the load resistor, and it must be added to the power delivered to the internal resistor. Therefore the total power is just P is equals to the I squared R plus the power delivered to the internal resistor. Right, now let us just do the following quick quiz in order to make sense of what we've just said in the previous slides. To maximize the percentage of the power from the EMF of a battery that is delivered to a device to the battery, what should the internal resistance of the power of the battery be? It should be as low as possible. It should be as high as possible. The percentage does not depend on the internal resistance. Now, in order for us to answer this question, now we just have to go back to that equation. You remember that the total power is nothing else but is the power delivered to the load resistor plus the power delivered to the internal resistor, and this is nothing else but is just I times the EMF, and this one is I squared R plus I squared small r. Now if we want to deliver more power to the load resistor, what should be the internal resistance be? As a result, this R must just be as slow as possible. It must be as slow as possible in order for the total power delivered to the load resistors to be higher. So as a result, the answer for that quick quiz must therefore be number A. Right, now let us also do the following example. The terminal voltage of a battery has an EMF of 12.0 volts and an internal resistance of 0.0500 ohms. Its terminals are connected to a load resistor of 3.00 ohms. A. Find the current in the circuit and the terminal voltage of the battery. So this is very simple. Because we know the equation of the current. The current is just given by this equation here. Now you know all this. You just plug the values and then the current will just be 3.93 amps. Now what is the change in V? Change in V, we know that change in V is given by this equation here, epsilon minus I times R. Now the change in V is just given by 11.8 volts. But now the change in V can also be obtained. The change in V can also be obtained by that I is times the load resistance. Now if you do this, you shall be able to get the same values that you have already obtained from that equation here of change in V. Now if you do that, you can just see that the change in V can also be related to the load resistance or the load resistance, because this is just the same as this value there. Right. So that's how you solve that kind of problem. Now, number B of the problem calculates the power delivered to the load resistor, the power delivered to the internal resistor of the battery, and the power delivered to the battery. Now, this question can be solved by going back to the total power is just given by the total power from the battery, and plus is given by I times the power to the load resistors plus the power delivered to the internal resistor. Now we know what is I. We have already found I. We know what is R. Therefore, we can be able to get this, and then we can also be able to get that. And then from there, we can just add that and that to get the total power. Now, in other words, this is what you are just going to do in order to solve that problem. You know what is the current, because the current, you've calculated the current before, and then the load, this is the power delivered to the load, is just given by 46.3 watts, and the power delivered to the internal resistors is just given by 0.772 watts. Now the total power is the algebraic sum of the two, and it's just given by 47.1 watts. Right. Now, as the battery ages, its internal resistance increases. Suppose the internal resistance of this battery rises to. This is the case because you remember from the previous problem, the internal resistance of that battery was just given by 0.0500 ohm. Now, if this battery ages, therefore the internal resistance increases to that value of 2.00 ohm. Now, how does that alter the battery's ability to deliver energy? In that case, the current through the circuit will just be given by 2.4 ohm, because now the internal resistance value has changed. It's no longer 0.0500 ohm, but it's 2.00. Now, in that case, you will also be able to know what is the change in V, because the change in V is just given by that equation. But now the internal resistance has changed. Therefore, the change in V will just be given by 7.2 by 7.2 volts. Now, the power delivered to the load is just going to be given by 17.3 watts, but the power delivered to the internal resistor will therefore be 11.5 ohms. Now the total power will just be the addition of the algebraic sum of the two. Right. Now find the load resistance R for which the maximum power is delivered to the load resistors in the figure. Now in this, for us to solve this, we just have to go back and then try to write the total power. The total power is given by IE, which is nothing else but is just the power delivered to the load plus the power delivered to the internal resistance. But we know what is I. Now the question is actually asking us is just asking us about this. The total power delivered to the load. That is the power delivered to the load. The PR is just nothing else but it's just I squared times R. But we know what is a current. The current from the previous is just EMF R plus small r. That's your current. Now in this equation, you are just going to plug the current there. Now the current is just going to be E squared times R divided by R plus R, but they must all be squared. And now that is the power, the total power to the load. Now in this case, if you are being asked to calculate the maximum, or whenever you calculate the maximum power to the load resistance, therefore you just have, for you to get the minimum or the maximum, you just have to do the derivative of power with respect to R. Derivative of power with respect to R. And in that case, that must just be equals to that you must also take D over dr. Now, as you can see, now in that case, you've got r as a numerator, you also have r as a denominator. In that case, you can just use the quotient rule. You can just use the quotient rule to differentiate this. In order for us to use the quotient rule, I just want to remind you that, say the numerator is called f, and then the denominator is called a g. Now, suppose that we have a function h which can be defined in terms of f divided by g. Now, if you are being asked from mathematics, of course, to calculate the h prime is nothing else but is f prime g minus g prime. Now you leave f and then divided by the g squared. So this is the quotient rule. This is how you differentiate this kind of function. Or else you can also use the product rule, and if you want to use the product rule to differentiate that h, you will just have to write h in terms of f and g, the inverse of g. Now this is the product rule. Now if you use the product rule there, the product rule is just given by f prime, you leave g inverse plus g inverse prime times f. So this is how you solve, and then you can just choose which one you want to do. But as far as that problem is concerned, I decided to use that the product rule. Now I leave it to you to also use the quotient rule to also prove that the answer would just be the same. So in that case, you know what is the power delivered to the load. The power delivered to the load is given by that, and then if you replace I is just E squared, the I squared there. This is what you are going to have. This R is the same R there. Now in that case, you rearrange the equation because you want to get the maximum power. You have to differentiate power with respect to radius, to not radius, to the resistance. And now in that case, this is what you are going to have. But now if you take this to the numerator, you are just going to have -2 there, and then from there you can therefore use the product rule in order to calculate the R. Now when you do that and rearranging the equation, you will just find that the load resistor must just be equals to small r, which is nothing else but the internal resistor. That will be the maximum power that will be delivered to the load. So R must be equals to the small r. Now that's what you are going to have, and I also want to leave it to you to use the quotient rule to actually show that the answer will just be the same, and that can also be done very, very easily, right? Good. Now that's the power. Now when you go back to the equation of the load, you can just see that the power, because the power delivered to the load is just given by epsilon squared, the EMF squared times R divided by R plus small r square. But in this case, we have seen that this R must just be the same as big R. Now therefore in that equation, I'm just going to have epsilon squared and then big R. In here I'm just going to have 2 R but square. Why? Because R is just the same as R, then I'm just going to have 2. In that case, this is just going to give me E squared divided by 4R. Why 4R? Because this R will cancel 1 here, and then you will just be left with 1. Therefore the maximum power, the maximum power to the load will just be given to S E squared divided by 4R. Never mind, because this is just the same as E squared divided by 4R. Why that is the case? Because the R is just the same as that. So it doesn't matter which R are you writing in your equation, because R is just the same as R. So as a result, that's the answer that you are going to have for that equation. And now when you plot P as a function of R, this is the graph that you are going to have, and the maximum power is when R is just equals to R. That's why the maximum power, you find it at that point there, right? Now that's what you are going to have. Now let us also talk about the resistors in series. When two or more resistors are connected end to end, they are said to be in series. For a resistors combination of for a series combination of resistors, the current are the same in all resistors, because the amount of charge that passes through one resistor's must also pass through the other resistors in the same time interval. The potential difference will divide among the resistors such that the sum of the potential difference across the resistors is equal to the total potential difference across the combination. Right, now that's the current is just the same, the I is just the same, that is passing through R1 and R2. Right, now the change in V, however, is just the total change in V is change in V1 plus change in V2. But now I can use the change in V is equals to IR. When you use that, this is what you are going to have. But the change in V is just the current are just the same. Now, if the current are just the same, therefore, this current will cancel with the other one. What I'm trying to say there is you have the change in V. The change in V here, you have change in V is just equals to IR, is just equals to IR, and then for change in V1, you have IR1 plus IR2. I don't want to write I2 or I1, because I1 is equals to I is equals to I1 is equals to I2. As a result, in that case, these I's will just cancel each other, and as a result, what are you going to be left? We are just going to be left with R equivalent is nothing else but is R1 plus R2 for the resistors connected in series. So that's basically what you are going to have for the resistors connected in series. Now, if you have more than two, you are just going to add the algebraic sum of all the resistors in the circuit, right? So as a result, this is what you are going to have as your equivalent resistance. Now, the equivalent resistance of a series combination of resistors is an algebraic sum of the individual resistance and is always greater than any individual resistance. If one device in series circuit creates an open circuit, all devices are in operation because because it is just going to be an open circuit. For example, in the previous circuit, if you make one resistor to be an open circuit, you just cut it, and then the whole circuit is not going to be in operation, right? So now the two resistance can just be replaced by one equivalent resistor, and the effect of this circuit is just the same as the effect on this other circuit on your right hand side, right? Now, a local change in one part of a circuit may result in a global change throughout the circuit. As I've said, suppose that you cut one resistor, and now the whole circuit is not going to be operational. For example, changing one resistor will affect the current and the voltage in all the other resistors and the terminal voltage of the battery. In a series circuit, there is one path for the current to take. In parallel circuit, there are multiple paths for the current to take. Right, let us also do the following quick quiz. With the switch in the circuit of the top figure closed, there is no current in R2 because the current has an alternative zero resistance path through the switch. There is a current in R1, and this current is measured with the ammeter, a device that is used to measure current at the bottom of the circuit. If the switch is open, the bottom figure, there is a current in R2. What happens to the reading in the ammeter when the switch is open? Now the question is actually asking you what is the the effects on the current. Now from there, I will just have to use this results of the Ohm's law, which is just equals to IR. Now in this case, I just want to write this in terms of the current. The current is just equals to change in V divided by R. Now if all these things are connected in series, if these resistors are connected in series, it will mean that the R equivalent will just be greater. Now if R equivalent is greater, therefore the current is just going to be small. The current will decrease. So that's what is going to happen. Now the reading goes up, the reading goes down. The reading will go down on the ammeter because the current will be decreasing. All right. Therefore, that is just going to be the answer for that quick quiz. Now let us also talk about the resistors in parallel. The potential difference across each resistors is the same because each is connected directly across the potential across the battery terminals. The junction is the point where the current can split. The current I that enters a point must be equal to the current that is leaving that point. Now that is, for example, the total current is just equals to I1 plus I2. Now the currents are generally not the same in each of the resistors, especially if those resistors are having different resistance, unless if the resistors are having the same value of resistor or the same value of the resistance. Therefore the current will just be the same. Now consequently, this is just a consequently of the conservation of energy. Right. Now what does this say? It is just telling us that the total current is nothing else but is just given by I1 plus I2. But now the potential difference is just the same. So in this equation, I just want to write this in terms of I. Now I'm just going to have the change in V over divided by, that must be divided by R equivalent, which is nothing else but it's just going to be change in V divided by R1 plus change in V divided by R2. Now in that case, because this change in V is just the same, they will just cancel. Now as a result, you will just be left with 1 over R equivalent for resistors connected in parallel is just going to be equals to this. The inverse of the equivalent resistance is just equal to the inverse of R1 plus the inverse of R2. So that is the combination of the resistors connected in parallel, which is the same as the capacitors connected in series. Right. So that's, and we can also replace the whole two resistors with just one single R equivalent. Now in that case, the equivalent resistance is just given by this, as I've just shown you in the whiteboard. The inverse of the equivalent resistors of the two or more resistors connected in parallel is the algebraic sum of the inverse of the individual resistance. The equivalent is always less than the smallest resistors in the group. Right. Now in parallel, each device operates independently of the other, so that if one is switched off, the other remains on. In parallel, all of the device operates on the same voltage. The current takes all the path. The lower resistance will have higher current. Even every high resistance will have some current. For example, household circuits are wired so that electrical devices are connected in parallel. And this is one of the questions that we were being asked in your Ohm's law practical, the online practical from Ohm's law. I think one of the quiz was asking you about the connection in your household circuits. Right. Now let us also do the following quick quiz. With the switch in the circuit of the top figure is open, there is no current in R2, there is a current in R1. However, and it is measured with the ammeter at the right side of the circuit. If the switch is closed, the bottom figure, there is a current in R2. What happens to the reading in the ammeter when the switch is closed? Now the question is just asking what happens to the current. Now in this case, we just have to go back to the resistors connected in parallel. Now we know that when the resistors are connected in parallel, for example, I'm just going to write change in V is just equals to IR. Now for the resistors connected in parallel, and if I want to write the current in this equation, therefore I'm just going to have I is just given by the change in V divided by R. But now for the resistors connected in parallel, the R equivalent is just going to be less than, the resistance will just be less than any of the resistors connected in parallel. As a result, if R is becomes low, therefore the current will just be high. Therefore the current will just be high. As a result, the answer for that quick quiz, it must therefore be telling us that the current will increase. Now the reading will increase, therefore the reading on the ammeter will increase as the current is also increasing. Right, let us also do the following quick quiz. In the figure, a third resistor is added in series with the first two. What happens to the current in the battery? As you know that the current, you remember the current is just given as change in V divided by R. But for when resistors are connected in series, when resistors are connected in series, it means that the resistance become high. Now if the resistance become high, the current will become low. So as a result, the answer for that quiz is when the resistance become high, because if you add another resistor R3 in series, it will mean the resistance become high. Now if the resistance become high, what happens to the current? The current will decrease. Yes, the current will decrease. Yes, the current will decrease, because if this becomes high, if that becomes high, it will mean therefore the I becomes low. That's basically what it means. Let us also do the following a quick quiz. What happens to the terminal voltage of the battery? What happens to the terminal voltage of the battery? Now what happens to the terminal voltage of the battery? Now I'm just going to write the change in V is just equals to IR. Now if the resistor it becomes big, the terminal voltage must also become high. If you increase resistor, because of this equation, as a result, the answer for that quick quiz, therefore it increases. Right. Now what happens to the current in the battery? The current in the battery, when they are connected in parallel, what will happen to the current in the battery? Now we know what is the current. The current is just given by the change in V divided by R. Now the equivalent resistance will always be lower when the resistors are connected in parallel, because 1 over R equivalent, you remember in that equation. So this is what we are going to have. Now as a result, now when these are connected in parallel, this is just going to be low, and when this is low, it makes the current to be high. So as a result, the answer for that will just make the current to be what happens to the current? The current increases. Yes, the current will therefore increase. Therefore, as a result, the answer for that quiz will just be A. Right, let us also do the following example of finding the equivalent resistance. 4 resistors are connected as shown in the figure, as shown in this figure 1, 2, 3, 4. These are connected in series and these are connected in parallel. Now find the equivalent resistance between point A and B, between point A and point C. Now as a result, these are in series, you just add them algebraic. This is what you are going to have, 12. Now these are connected in parallel, they are equivalent, therefore this is just going to be 2 ohms, and these are now connected in series. Now if you add them, it's just going to be 14. They are equivalent, therefore of the whole resistance is just going to be 14.0 ohms. Now this is what you are going to have for the R equivalent. The R equivalent will just be 14 ohms, because you are just going to add these two, and this is for the one connected in series and this is for the one connected in parallel, and then the R equivalent will just be given as 12 ohms, because it's just going to be 12 plus 2 is just going to be 14 ohms. Right. Now the next question is saying what is the current in the each resistor if a potential difference of 42 volts is maintained between A and C. Now the R equivalent, we know what is the R equivalent, therefore we can just use the equation of the change in V. We can just use the I is equal to change in V AC divided by R equivalent, because we know what is R equivalent. The R equivalent is just 14 ohms. Now if you do that, what are you going to have? If you do that, this is what you are going to have for the current through the resistor, 8 ohms and then 4 ohms. Now in that case, for the change in V for this resistor and that other resistor, the change in V1 is just the same as the change in V3. But what we are seeing there is the fact that this resistor is double that resistor. As a result, the I2 will just be equals to 2I1. Now in that case, the change in V1 is just going to be 3 times I1, it's just going to be 6.0 times I2, which is nothing else but it's just going to be the same as the 3.0 times the I2. Right. Now, this is just because we know that the magnitude of this resistance is twice the magnitude of the other resistance. Therefore, I2 will therefore be equals to twice I1, because these resistors are actually connected in parallel. Now, in that case, you can just write the equation for the, because you know what is the total current. Total current is just current passing through the 8 ohm resistor and 4 ohm resistor, but now when it's there, it's just split. But knowing that I2 is just equal to twice I1, therefore we can be able to get the value for I1 by I1 plus I2 is just equal to 3, and then I1 plus 2I1 is just equals to 3. Therefore I1 is just equals to 1 ohm. It's just equals to 1 m. Now I2 will also be equals to 2 times I1, 2 times I1, which is nothing else but it's just going to be given as 2.0 amps. Now the change in the potential of BC, the change in potential BC will just have to be calculated from the one of this resistor. But now when you use this resistor, you have to multiply by the I1. But if you use this resistor, you have to multiply by I2. As a result, this is just going to be given by 6 ohm. Right. Now because I1 is just 1 and then I2 is just 2, as a result you are just going to have 6.0 volts. Now the change in AB, the change in the potential difference in AB is just the equivalence resistor times the I. The I is 3 ohm, therefore this 12 times 36. Therefore, the total change in the AC would just be the algebraic sum of these two, and then you are just going to have 42 volts as the change in the potential difference from A to C. Right. Now let us also do the following good example for the resistors in parallel. 3 resistors are connected as shown in the figure. A potential difference of 18 is maintained between point A and B. Calculate the equivalent resistors of the circuit. Because they are connected in parallel, you just use that equation and then you plug the values and then you end up with the R equivalent. And then from there, the part B is saying find the current in each resistor. Now in order for you to get the current in each resistor, because they are connected in parallel, the potential difference there is just the same as the potential difference of the battery. Now in order for you to calculate the current on each resistor, you just have to use the resistance on each resistor. As a result, this is what you are going to have as your I1, and then your I2 is just going to be 3 and your I3 is just going to be 2. But now if the question was also asking you the total I, the I, what is the value of I? The I is just nothing else but it's just I1 plus I2 plus I3. The algebraic, when you add that, because the current into must just be the same as the current out of this junction. Right. So that's what you are going to have for that. The I will just be the algebraic sum of all this currents passing through each and every resistor. That means that the I is just the same as I1 plus I2 plus I3. Right. Good. The part C is calculate the power delivered to each resistor and the total power delivered to the combination of this resistor. Now, we know what is the current through each and every resistor, and then we are just going to be using, because we know what is the power. The power on each resistor is just I times this R. Now it must be square. We know what is the current on each resistor, therefore we are just going to use that equation to calculate the individual power delivered to each resistor, and then we can just add the algebraic sum. For 3 ohms, this is what you are going to have. For 6 ohm, this is what you are going to have, because the current that is passing through 3 ohms is 3.0 from the previous example, and for 9 ohms, the current that is passing from 9 ohms is 2.00 amps. Therefore you multiply that, and then the total power delivered to the whole resistor, it must just be the algebraic sum of all the resistance. Therefore this is what you are going to have, or else you can just have this power by using this equation that we have derived in the previous chapter, that is change in V squared divided by R equivalent, therefore is just the same as the total power that we are just adding algebraic sums of this. So that's how you solve this problem. Now the other part of the question is saying, what if the circuits were as shown in the figure B instead? How will that affect the calculation? Now this circuit, when you look at this circuit, the battery is applying the potential difference between point A and B, and it is actually the same as this circuit, so there is not going to be any difference. There will be no any effects, because the battery still maintains the potential difference of 18 volts between point A and B. So the two circuits in the figure are electrically identical. Right, let me also introduce you to Gustav Kirchhoff. Now he was a German physicist who actually worked on the spectroscopy. He founded the science of spectroscopy, and he also discovered the two elements in your periodic table, which is cesium and ruthenium. He invented also the astronomical spectroscopy. Now the Kirchhoff's rules, there are ways in which resistors can be connected so that the circuits formed cannot be reduced to a single equivalent resistor. Two rules called the Kirchhoff's rules can be used instead. Now the first rule for a Kirchhoff's rule is the junction rule. The sum of the current at any junction must equal 0. Currents directed into the junctions are entered into the equation as a positive current, and those leaving at the junction as minus I. Now a statement of conservation of charges, of course. Right, now the mathematical description of this junction rule is just the sum of the current in a junction is just equals to 0. Now for example, if you have the I1 must be the same as the I2 plus I3. This is what this equation is just saying. This is the requirement by the conservation of energy, and this is just nothing else but it's just similar to the water flowing in the pipe like this. Now the water that is flowing must just be equal to the water that is actually flowing out of the junction. Of the pipe. Right, now the other rule for Kirchhoff's rule is the loop rule. A loop rule, the sum of the potential difference across all elements across any closed circuit loop must be 0. A statement of conservation of energy also, and the mathematical description of that is just the sum of the closed loop change in V is just equal to 0. You will just see what am I referring to when I'm saying a loop or a closed loop in a short while when we are doing one of the examples using requiring us to use the Kirchhoff's law or rules. Right, now this is the sign convention that I want you to be able to remember. For an example, if you move from point A to B, and then while you are moving from point A to B and the current is also moving in this direction, therefore the change in V in that case is just going to be given as minus IR. Right, but when you are still moving from point A to B in an opposite direction to the current, when the current is moving from B to A, now the change in V is just going to be positive IR. Now when you are moving from A to B and then you are moving from a lower terminal of the battery to a higher terminal of the battery, the change in EMF is just given by positive E. Now, when you are moving from A to B, and then you are moving from higher terminal to the lower terminal, from positive terminal to negative terminal, the change in V is just given as negative E, negative EMF. Right, let me just repeat them again. When moving from point A to B in the same direction as the current is moving, the change in V is just equals to minus IR. But when you are moving from A to B in an opposite direction to the current, therefore the change in V is just positive IR. When you are moving from A to B, and then you meet the EMF along the way, and then you are moving from the lower terminal to a higher terminal, the change in V is just positive EMF. Now, when you are moving from A to B, and then along the way you meet with the EMF, and then you are moving from the higher terminal to the lower terminal, the change in V is just given as minus EMF. And this is very important, and this is what you have to memorize, if I must say, because this is not going to be given in your test or in your exam. So it must always be in your head. Please just memorize this, and which is very simple to actually memorize that. Right, you will just see when we are actually doing the example. Now, you use the junction rule as often as needed, so long as each time you write an equation, you include in it a current that has not been used in the previous junction rule equation. In general, the number of times the junction rule can be used is one fewer than the number of junction points in the circuit. The loop rule can be used as often as needed, so long as a new circuit element, resistor or battery, or a new current appears in each new equation. You need as many independent equations as you have unknown. What does that mean? You need 2 equations for 2 unknowns. You need 3 equations for 3 unknowns, and so on. 4 for 4 unknowns. 5 equations for 5 unknowns, and then you solve them simultaneously, and then you will be able to get the values of each of any element of the question that is being asked. Right, now, in order to solve a particular circuit problem, the number of independent equations you need to obtain from the 2 rules equal the number of unknown currents, and any capacitor acts as an open branch in the circuit. The current in the branch contained the capacitor is 0 under steady state condition. Right, let us also do the following example of a single loop of a circuit. When I'm talking about the loop, as I've said previously, is a single loop circuit contains 2 resistors and 2 batteries as shown in the figure. Neglect the internal resistance of the battery. Find the current in the circuit. When I'm talking about the loop, is I'm moving from A and then I'm going back to A. That's a loop. That's a loop. In some other circuits, you might have more than 1 loop, or you might have 2 or 3. It will just depends on the circuit's structure. So in this case, you move from A, you go back to A. Now that's a 1 loop. Now in this case, when you move from A, you go to B, you see that the change in the potential difference is just going to be positive, because you are moving from lower to the higher terminal. Therefore, E1 will just be positive. Now, when you are at C, you are just going to have minus IR, because there will be a voltage drop there. But now, when moving from C to D, there will be you are moving from higher to a lower terminal. That will be minus E2. And when you are moving from D to A, to close the loop, because you are moving from A to A, it's just 1 loop, that will be minus IR. As a result, this is what you are going to have for that equation. Now, moving from there to there is just going to be positive, because I am moving from lower to a positive, from lower terminal to a higher terminal is just going to be positive EMF. That's why you are seeing positive E1. And then from there, I am moving from B to C. Now from B to C, I am moving in the same direction as the current. Therefore, I'm going to have minus IR1, because this is resistor is named R1. But now when I'm moving from C to D, I'm moving from higher terminal to the lower terminal. Therefore, I'm just going to have lower terminal. I'm moving from higher terminal to the lower terminal, from higher terminal to a lower terminal. I'm going to have minus A2. That's why you have minus A2. From D to A, in the same direction of the current, I'm just going to have minus IR2. Now, in that case, you can just rearrange the equation, and then when you rearrange the equation, if the current is moving in this direction, you can be able to get the value of I, because the I is just going to be given by that. Now, in that case, if you plug the values, you are just going to have minus 0.33A. And this minus is actually signifying that the direction of the current was chosen wrongly. It means that the current is not moving clockwise, but it is moving in the opposite direction, anti-clockwise. Now, in that case, I leave it to you to actually do this equation where the current is not moving in this direction, but is moving in this opposite direction. Now, if this current is moving on the opposite direction, everything will just be the same, but the signs for E1 and E2 will just be an opposite signs. As a result, the answer there, you are just going to have a positive 0.33A, and then I leave it to you to do it. Right. Now, what if the polarity of the 12 volts battery was changed? Now, the polarity there is now changing to be like this. Now, if the polarity is going to change like that, this is what you are going to have. Instead of having minus there, you are going to have plus. Now, as a result, the current through is just going to be 1.0, which is totally different compared to the previous current that we obtained. Right. Now, find... this is another example where you have two loops. You have two loops. For example, I can be moving from A to A in that loop, and then I can be moving from B to B on the other loop. Now, this is the second example. Find the currents I1, I2, and I3 in the circuit shown in the figure. Now, in this case, I'm just going to write this equation as I3 is nothing else but the junction rule is telling us that I3 is just I1 plus I2. I3 is just equals to I1 plus I2. Now, from this loop of AB, ABCD, ABCD, then I'm just going to have A, B, C, D. Now I'm moving from lower to higher. I'm just going to have positive 10 volts. But now when I am there, I'm going to have I1 times 6.0, but it must be minus 6.0 because I'm moving in the same direction of the current. That will be minus I that, and then in here it is just going to be minus, but the current that is moving in this 2 ohm, in that 2 ohms is I3, is no longer I1. Therefore, that will be minus 2 ohm times I3. That's the first equation from this loop. Now I'm going to develop another equation for this other loop. I have what first equation, that's my second equation. Now the third equation is I'm going to derive it from this other loop of BEFCB. Now BEFCB. Now if I am moving from B to that direction, I'm just going to have minus 4.0 times I2. And then when I am there, moving from higher terminal to the lower terminal, I'm just going to have minus 14 volts plus, in this case, I'm just going to have plus because the current I1 is going in this direction. Now that loop, I'm moving in this direction. Now it will be plus 6.0 times I1. And then when I am here moving from higher to lower, that will be minus 10 volts. Now 14 minus 10 is just going to give me minus 24. So this is first equation, and then I have second equation. I also have the third equation here, and then I also have 3 unknowns. So the equations are enough for me to solve the values of I1, I2, and I3. Right. Now in that case, we know that I3 is equal to I2 plus I1. Now this is what you are going to have from the first equation. From the first equation, this is what you are going to have. And in that equation, I'm just going to replace the value of I3 because I3, I know what is I3. I3 is I1 plus I2. Then this is what I'm going to have in that equation. And from there, if you simplify this equation, you are just going to have this equation because this I1 will actually combine with the other E1. That's why you are having the 8 ohms here because it's 6 plus 2 for I1. Therefore, you are going to have 8. And the 2 I2 times this I2. That's what you are going to have for that equation. Now, from the previous equation that we have already derived, I'm going to multiply that equation by 4. You will see why I'm multiplying it by 4. On the other loop, I multiply that by 4. This is what I'm going to have. Now, this equation that I'm having here, I'm going to multiply it by 3. If I multiply this equation by 3, this is what I'm going to have. Now, I add that equations to the other equation. Therefore, if I add that other equation to that other equation, I'm just going to be able to find the value of I2. Now, the value of I2 is just given as minus 3.00. The I2, therefore, it means that the I2 is actually not going down, but it is going the anti-clockwise direction. Now, if I have I2, then I can use one of the equation to actually get the value of I1. And then if I know the value of I1, I can just add I1 plus I2 in order to get the value of I3, because the value of I3 is nothing else but is just I2 plus I1. Now, the negative sign also signifies that the I3 is not going in this direction, but it is going in the other direction. Now, I'm going to leave it to you to play around with this and change the direction of the current, and then use the Kirchhoff's law. You will see that you, instead of having minus here, you'll have positive. Instead of having positive here, you'll have minus, and that's what you are going to have for the values of the current through this circuit. Now, with that, good people, I would like to pause there, and this are your tutorial problems. I think I need to pause here, and then keep well, and see you next time. Bye bye.